this is VLSI data conversion circuits lecture 52. In the last class we were discussing the relative merits of binary weighted and thermometric DACs. The sigma DNL in the binary weighted case was approximately square root of 2 to the n times sigma g by g, whereas in the thermometer case was square root of 1 times sigma g by g, whereas the sigma INL is the same in both cases. The upper result makes intuitive sense because in the binary weighted case the worst case DNL, please note that these are all worst case numbers. In the binary weighted case the worst case occurs at the major code transition, and it is during the major code transition that you are getting the next step by removing or disabling a whole bunch of current sources, I mean in this case conductances, and enabling another set of conductances which is only marginally greater than the one that you have disabled. So, on a more commonsensical level, it is trying to get a very small number by subtracting two large numbers, each of which is uncertain, right, which means that the result, which is the difference, is very uncertain because the uncertainty of both the random numbers, both the big and the small, I mean of both the big numbers adds, giving you a lot of variance. On the other hand, the INL is simply measuring the deviation of the code from the ideal code, and that if you wanted a code of M, it means that whether you do it binarily or through a thermometer, M current sources must be, M conductances must be active, which means that the INL must be the same in both cases, because you are basically measuring the deviation of M conductances from M times G, right, and whether that is binary or thermometer remains the same, alright. So, which means that as a designer, if you want to hit a certain target DNL, a certain worst case DNL, then if you implement it as a pure binary weighted system, you will need to have a much tighter matching requirement on the individual elements, right. I mean clearly to get a certain sigma DNL for the binary weighted case, the sigma must be square root 2 to the n times smaller than what it would be otherwise, when compared to the thermometer case, alright. Okay. Now, one question that one might ask is, alright, let us say I implemented a resistor or a conductance and its nominal conductance is G. Now, there are variations due to random mismatch, and the factors that cause mismatch are the following. One, in a resistor what happens is that these edges are not sharp, and that is one source of variation. Then there will be some tolerance to the way you can define the length of the resistor, and there will be some tolerance to W. So, W and L being random variables, and there is a edge roughness and so on, all these things basically when you put them all together you can model the whole thing as some Gaussian random variable with some variance. Now, if you want to get a conductance G, but with improved matching, what do you think you can do? Increase W and L, and why does that make sense? Okay, so you can think about it in a couple of ways. One argument you can make is that the delta L and the delta W probably remain the same, but if you make L much larger, the delta L becomes a much smaller fraction of L, and therefore you can expect improved matching, and that is generally correct. So, the matching is dependent on 1 over square root W L. Okay, the sigma G by G will be proportional to 1 by square root W L, and this is not just noticed with resistors, it is also noticed with capacitors and transistors. Okay. And one more way of looking at it is to say that if I took 4 identical resistors conductances and connected them up like this, G, G, G and G, what is the conductance now? This has this is equivalent to a single conductance G. However, what can you say about the variance of this composite conductance? Each of these, as say this is delta G1, this is delta G2, delta G3 and delta G4. The conductance of the top branch is what? G plus delta G1 into G plus delta G2 divided by 2G plus delta G1 plus delta G2. Oh yeah, that is where I made the mistake, correct, which is 1, which is G times 1 plus delta G1 by G times 1 plus delta G2 by G divided by 1 plus delta G1 plus by 2G plus delta G2 by 2G. Yeah, that is the mistake, right, correct. I am sorry, I made a mistake. This is G by 2 times approximately 1 plus delta G1 by 2G plus delta G2 by 2G. Right, these are all small numbers, so I can pull them up into the numerator and then subtract and so on. So, the top branch has a conductance which is G by 2 plus delta G1 by 4 plus delta G2 by 4, and similarly the lower branch has a conductance G by 2 plus delta G2 G3 by 4 plus delta G4 by 4, and when you add the two you get a conductance G plus a random variable which is sorry, that is I made another mistake now. So, 4 and 16. Yeah, yeah, this is right. So, it is n of 0 sigma G by G times 1 half, G times 1 plus alright. So, variances add, so it is 1/16th and you have 4 of them, so it is 1/4. So, the standard deviation must become square root of 1/4, which is 1 half, alright. So, you have a conductance which is 4 times larger and its variances, the matching is improved by a factor of, the sigma has gone down by a factor of 2, alright. So, in other words, if you want increased matching, you must be prepared to have a physically large element, whether it is a transistor or whether it is a capacitor or whether it is a conductance, alright. Improved matching means larger area. Okay. So, while I have discussed this binary versus thermometer decoding in the context of a resistive DAC, the same is true for whether you use capacitors, where then the quantity of interest is not I DAC, but charge Q DAC, alright. So, you have capacitors which are charged to some voltage, and then you somehow take many of those capacitors and then add up or extract the charge from all these capacitors, just like how we are passing current through these resistors and extracting the current. It is also possible to do that with charge, alright. And again, just like how matching depends on the matching of the resistors, there it will depend on matching between capacitors, and the same arguments for area and matching will hold, alright, and the same arguments for the LSB change, or rather the DNL of the DAC will hold, whether we implement a completely thermometer type design or a completely binary weighted design. And since we have seen the two extremes, which are the thermometer code where the DNL is very nice, but the INL, and I mean the INL is also, there is no difference between the thermometer and the binary designs as far as INL is concerned. However, the decoder is a lot less complex in a binary design, but you get a lousy DNL, right. So, in the 4-bit example that we have seen, the decoder may not seem like a big deal, right, because it is only a 4 to 15 decoder. Now, imagine you want to design a 12-bit DAC, then the decoder complexity becomes 12 lines coming out and 4096 wires getting out, which makes routing and everything else a terrible nightmare, right. So, one obvious thing is to say, hey, is there some middle path where I do not have to deal with the enormous complexity of routing 2 to the n wires, which is what I should do in a fully thermometer design, right, and B, the terrible DNL I will get if I use the same kind of elements in a fully binary weighted design, where I have gotten rid of the decoder, but the DNL will be terrible. So, in order to make the DNL come within spec, I will have to choose elements with lot better matching, which means that the elements have to become much bigger, as we just saw, which means that the design will become occupy a lot of space, you understand. And to add to this, we are trying to meet the DNL specs by increasing the matching of the design, alright. Unfortunately, the INL spec is way over designed, right, because INL is only proportional to, I mean as we saw before, thermometer or binary, the INL worst case expression is the same. Okay. So, it is likely that if we go and design for good DNL in the binary case, the sigma g by g will have to be chosen to be so low that the INL may be way over designed. You may not really require such a good INL at all in the system, right. And the, I mean the penalty of paying for easy decoding is this huge area as far as the, or the improved matching requirements on the elements. Now, the question is, can we find a middle path where you have neither the enormous decoding problems associated with a fully thermometer design, nor the terrible DNL associated with a binary design. Okay. And I mean as you guessed, it is, you do a partly binary plus partly thermometer decoding, and this kind of DAC design is called segmentation or segmented DACs. All right. So, as an example, let us take a 10-bit DAC and say I am going to segment it such that half of it is binary and half of it is thermometer. So, let us say B9 through B5, or rather B5 will be decoded one way and B4 through B0 decoded in an other way. So, do you think it makes sense to decode the LSBs in a binary manner or in a thermometer manner? In other words, should we decode the MSBs in thermometer and LSBs in binary or vice versa? Pardon? MSBs must be in
binary.
Binary. Why?
It requires lot of bytes.
Pardon?
It requires lot of bytes.
No, if I say that I am going to split the DAC into two parts, one I am going to decode 5 bits binary and 5 bits thermometer. From a decoding point of view, it does not seem to make any difference, right. If you decode one binary, the other will be thermometer and so on. All right, maybe the 10 bits is confusing you. Let me go back to the 4-bit example. All right. So, I can conceive of at least two ways of segmentation. Let me choose a 2-bit plus 2-bit segmentation. Right. So, B3, B2, B1, B0. I am going to say, I am going to, as somebody points out, I am going to say let me try and do this binary and the LSBs I am going to do as thermometer. Let us see what happens, correct. So, in other words, the DAC will look like this. So, I will continue to have what should I have? If B3 and B2 are decoded in a binary fashion, I should have 8G and 4G. So, this gets controlled by B3, this gets controlled by B2, and what about B1 and B0? I will have 3 individual conductances, all of value G, okay, and all I need to do is have a decoder which takes B1, B0 and goes and controls these switches, and this is I DAC. All right. So, what is happening with the biggest problem with the DNL is the is resistor mismatches, all right, and at what code transition is the problem the worst? Zero followed by all ones to 1 followed by all zeros. So, has anything changed when it is 0 followed by all ones? The current will be G times B ref times 7 plus delta G4 plus delta G2, delta G plus delta G 1A, 1B, 1C, okay, where I call this A, B and C. Okay. Does it make sense? Now, if it is 1 followed by all zeros, what is the output code? Output value corresponding to this code, G times V ref 8 plus delta G, or rather this must be, all this must be, or I should get rid of delta G8. Correct. So, what is the variance of the step size? It is still 15. Please note that fundamentally it should not make any difference, because how are we getting the step? We are turning off all these characters and turning on the 8G, which is exactly the same thing that we were doing before. You understand? So, clearly making the MSBs get, decoding them in a binary fashion is not the right thing to do. Intuitively this is what is happening in the ideal DAC outputs must be like this, okay, where I just joined the horizontal lines just to make sure that we see something there rather than just dots. Now, with a binary weighted DAC, right, if this particular transition was the major code transition, this will be way in error. So, this step for instance can become like this, okay. This is the major code transition, and you will have large DNLs at not just, the largest DNL will be at the major code transition, but every sub major code transition, if you will, right, whenever any of the lower bits change, whenever there is a change from zeros followed by all ones to 1 followed by all zeros, even at the, for example, there will be a peak in the DNL at 0 followed by all ones and 1 followed by all zeros, but there will also be peaks, local peaks in the DNL when you get 0 0 1 1 1 to 0 1 0 0 0. This the variance of this peak will be smaller, right, but there will still be a peak, you understand. So, in other words, the use of the binary decoder will make large amounts of will cause large amounts of DNL, and it does not help if the LSBs are decoded in a thermometric fashion. Does it make sense? Okay. So, another way of understanding this is B3 B2 is a defines a how many bit DAC is a 2 bit DAC with a large step size of 4G times Vref, correct. Now, if this staircase, which is ideally supposed to be like this, is made with a binary decoding, then what will happen is that this step will become very large or very small depending on the deviation of the individual elements. Okay. Within this step, within this large step, the small guys are jumping, helping you jump from one large step to the other, correct. Decoding them in a thermometer fashion will ensure that that small staircase which is joining one, which is helping you go from this step to this, right, that staircase will be very uniform, but the big staircase has got a lot of variation at the major code transition, right, you understand, and you can see that the variance is no better than the fully binary case. So, in other words, when you want to segment, therefore, you must segment the MSBs must be thermometer decoded, okay, which means that you can always think of a DAC as the DAC output as coming from 2 DACs, one which is decoding the MSBs and one which is decoding the LSBs, and you add the 2 up together, right, that is mathematically that is a perfectly valid point. Now, the LSB size of the MSB DAC, the step size of the MSB DAC is much larger than the step size of the LSB DAC. So, if you want to make an overall nice staircase, would you want to make a good staircase for the MSB DAC or for the LSB DAC? You want the big staircase to be as linear as possible, and the small DAC, the DAC which is decoding the LSBs is just creating another staircase between two levels of the MSB DAC, correct. So, if there is a jump in the DNL in the small staircase, that jump is likely to be small because the staircase itself is very small, whereas for the MSB, the DAC decoding the most significant bits, since the height of the staircase is large, you want to make sure that is a lot more uniform than the LSB. Ideally, you want to make everything uniform, but that, as we saw, will lead to a complete thermometer implementation, which makes the decoder a nightmare. You understand? So, is this clear that the MSBs must be decoded in a thermometer fashion, right. So, if the MSBs are decoded in a thermometer fashion, then we will have the decoder here, B3, B2, and what must each of these conductances be? 4G, okay, and the LSBs are decoded in a binary fashion. So, this must be 2G and G, and this will be controlled by B1 and this will be controlled by B0. Does it make sense? So, now what is the within quotes error in the step size at the major code transition? At the major code transition, in other words, when we go from all 0 followed by all ones, what is happening? Which all are on? This is on and one of these guys is on, okay. And so, the step size will be, or the output level will be 7G plus delta G2 plus delta G plus delta 4G or delta G4 A, and when the code jumps to 1 followed by all zeros, it will be Vref times 8G plus delta G4A plus delta G4B. Okay. So, what is happening when the code becomes 1 followed by all zeros? This is getting turned on and those two are getting turned off. You understand? I mean, here also there is a difference between you are realizing that G by taking the part of it is realized as a difference between two large numbers. However, those two large numbers are not quite as large as they would have been if I did a complete binary decoding. Is that clear? That will become apparent when you do the subtraction. So, what is the difference? Is Vref times G plus what variances add? Thankfully, this does not come into the picture because it exists in both cases. So, this becomes G plus delta G4B plus delta G2 plus delta G. So, the variance therefore sigma DNL has now become square root sigma G by G times square root 7. What was earlier square root 15 has become square root 7. Does it make sense? Right. So, what can you say about sigma INL? Sigma INL remains the same. Okay. So, if you segment too little, what does it mean? Pardon? Yeah. So, as you keep changing the degree of segmentation, which is defined as the number of bits, I mean clearly it is established that it makes sense when you segment, it makes sense to make the MSB portion thermometer coded and the LSB portion binary coded or binary decoded rather. So, you can define the percentage segmentation as, if it is completely binary you call it 0% segmentation, if it is completely thermometer you call it 100% segmentation, and therefore, depending on the number of bits you code or you decode in a thermometer fashion, you define a percentage segmentation which ranges from all the way from 0 to 100. Okay. And as you keep increasing the percentage segmentation, whether if it is 0, this is a completely binary weighted design, and if it is 100, it is thermometer decoded design. All right. What happens to sigma INL as you change the percentage segmentation? Sigma INL remains the same. All right. And what happens to the sigma DNL? The worst case DNL or sigma DNL goes down as you go on increasing the percentage of segmentation, right. So, we will continue with this in the